Today we're gonna talk about the chemical reactions and the calculations associated with the chemical reactions. But first we need to introduce the concept of a mole. So what is the mole? The mole is a counting term. So what does that mean? Counting term is used to state a number of certain items. A dozen of pencils, a dozen of eggs, or a ream of paper, which is 500 sheets, or one gross of pencils, which is 144 pencils, and so on and so forth. So what is the mole? Mole counts small particles such as atoms, molecules, or ions. The mole is also called Avogadro's number, is a unit that contains 6.02 multiplied by 10 in a power of 23 items. So in 1 mole of atoms, there are 6.02 multiplied by 10 in a power of 23 atoms. It was named after Amedeo Avogadro, the Italian physicist who first suggested to use this particular number. So 1 mole of an element contains this exact number of atoms of that element. If it's 1 mole of carbon, that exact number of carbon atoms. If it's 1 mole of sodium, same exact number of sodium atoms. In this table, you can see that a mole is always the same. 1 mole of water molecules will contain that exact number, 6.02 by 10 in the power of 23 molecules of water. The same is true for 1 mole of vitamin C, and so on and so forth. So you can write an Avogadro's number as a conversion factor. 1 mole contains 6.02 multiplied by 10 in the power of 23 particles, or 6.02 multiplied by 10 in the power of 23 particles in 1 mole. Now, when you look at the when you look at the formula of a particular compound, you can actually figure out how many moles of each atom are in 1 mole of a compound. So let's talk about it a little bit more. So the subscripts in the chemical formula show the relationship of the number of atoms in the formula. They basically demonstrate the number of moles of each element in 1 mole of a compound. So the formula for aspirin is C9H8O4, which means that 1 molecule of aspirin contains 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. Therefore, 1 mole of aspirin will contain 9 moles of carbon, 8 moles of hydrogens, and 4 moles of oxygen. The convenient parameter to use in the calculations is called the molar mass. It is useful to convert moles of an element to grams, or the other way, convert grams into moles. For instance, 1 mole of sodium has a mass of 22.99 grams. So how do we know what is the molar mass of an element? It turns out that the molar mass, the mass of 1 mole of an element, is equivalent to the atomic mass of an element expressed in grams. For instance, the atomic mass of carbon is 12.01, which means 1 mole of carbon weighs 12.01 gram. The atomic mass of lithium is 6.941, which means 1 mole of lithium weighs 6.941 gram. So in this presentation, we're going to round the molar mass to the 10th place, or you're going to be using at least 3 significant figures for our calculations. So this is some examples. Silver 107.9, so rounded to 10th. Carbon 12.01, sulfur 32.07, they're going to be rounded. So how do you calculate the molar mass of a compound? Because we already learned that the molar mass of an element is equivalent to its atomic mass expressed in grams. So to do the same for the compound, we take molar mass of each element and multiply it by its subscript. And then we add the results of such a multiplication. For example, if you want to calculate the molar mass of methane, you need to take molar mass of carbon, 12 gram, and add molar mass of hydrogen, which is 1, multiplied by 4. If you want to calculate molar mass of sulfur dioxide, you need to take a molar mass of sulfur, which is 32 gram, and add molar mass of oxygen multiplied by 2. Molar mass can be presented as a conversion factors. So here's the conversion factor for the methane that we already discussed. So the molar mass of methane is 16.05 gram, which means there are 16.05 gram of methane in 1 mole of methane, or that 1 mole of methane weighs 16.05 grams. So this is the guide how to calculate the moles of a substance from grams. So let's say you need to calculate the moles of a substance from the grams of a substance. Let's assume that you have 196 grams of sulfuric acid. I'm approximating the numbers. I round them to the without any decimals, only the integers. So first you need to calculate the molar mass. The molar mass of sulfuric acid will be 2 multiplied by the molar mass of hydrogen plus molar mass of sulfur plus 4 multiplied by 16, which is the molar mass, which is the molar mass of oxygen multiplied by 4. So at the end of the day, the molar mass of molar mass of sulfuric acid will be 98 gram. Then you write a conversion factor because you need to find moles. So you write 1 mole weighs 98 grams, and then you multiply it by 196 grams. Around 2, so 2 moles. We're talking about 2 moles of sulfuric acid right here. Chemical reaction describes the chemical change that occurs when a substance is converted into one or more new substances that have different formulas and different properties. So it may be observed by the different signs, not often they are present, but change in color, bubble formation, production of a solid, heat, production of a gas, basically, heat that's produced or absorbed. So here when nails rust, they change appearance, so that's the chemical reaction between iron and oxygen producing iron 3 oxide. So when we write a chemical reaction with several symbols plus separate 2 or more formulas in the reaction, reactants are written on the left side, and then the arrow is written and it directs to the products. Products are written on the right side. Okay, so here you can see the arrow. If we have that sign delta, delta indicates the heat. So this is how reaction would look, generic reaction. Two reactants heated up to make a product. Physical states of compounds are denoted in the parentheses after the compound, where S is solid, L is liquid, G is gas, and AQ is the aqueous, which means dissolved in water. The important feature of the balanced chemical equation is that there are no atoms lost or gained, and the number of atoms on the reactant side is equal to the number of atoms on the product side for each element. This is one of the most critical pieces of knowledge. If you have one carbon on the left, you gotta have one carbon on the right. If you have two oxygen on the left, you gotta have two oxygens on the right. Can't be any other way. So in order to balance chemical equation, we need to write equation using the correct formulas, then count the atoms for each element, the reactants and products, and use coefficients that are written before the formulas to balance each element. And then you got to check the final equation to confirm that it is balanced. So a quick example can be this. So you have ethane, which is oxidized, burned in oxygen, producing CO2 and water. So first we're going to balance carbons, so we have two carbons, two carbons. Then we're going to balance hydrogens, and we will have to write 3 here. Well, what you end up with is 2 oxygens on the left, and 7, 2 multiplied by 2, and 3 multiplied by 1, 7 oxygens on the right. So you will need to multiply this by 7, increase each coefficient by 2, and put 2 here. Now this reaction is completely balanced. Balancing reactions is more of a skill or art than any science. Now chemical reactions can be classified in 5 different categories: combination, decomposition, single replacement, double replacement, or combustion. So what happens in the combination reaction? In the combination reaction, 2 or more elements, we're going to be talking about 2 mostly, form one product. Or simpler compounds combine to form a more complex product. So here are some examples of the combination reactions. You see in each of these examples you have 2 original elements or compounds. So here you have 2 elements, and this one you have 2 compounds, and they form one product: magnesium oxide, sodium chloride, or sulfuric acid in this case. In the decomposition reaction, a substance splits into 2 or more products. Mercury oxide splits into mercury and oxygen. Potassium chloride splits into the potassium chloride and oxygen. In a single replacement reaction, one element takes the place of a different element in another compound. So here you have attraction between the zinc and hydrochloric acid, producing zinc chloride and hydrogen, or reaction of iron with a solution of copper sulfate, producing iron 2 sulfate and copper. But in a double replacement reaction, the positive ions in the reacting compounds switch places. So here you see silver and sodium, they switch places, forming the precipitate of silver chloride and sodium nitrate. When you create a reaction of zinc sulfide and hydrochloric acid, it forms zinc chloride and hydrogen sulfide gas, and zinc and hydrogen switch places. In a combustion reaction, the compound that contains carbon, specifically carbon, burns, and oxygen to form carbon dioxide in water. So for instance, propane burns in oxygen to form CO2 in water, or methane burns in oxygen to form CO2 in water, and it always releases energy. Energy is released as a product in the form of a heat. So this is some examples of reaction types and description of those reaction types. Now, another interesting separate class of reaction are called oxidation and reduction reactions. They're not falling into those 5 categories. I mean, this, for instance, this oxidation reduction reaction here, where iron is oxidized by oxygen forming iron 3 oxide, is a typical combination reaction, but it is also an oxidation reduction reaction. These type redox, also called redox reactions. They give us energy from food, provide electrical energy in the batteries, for instance, as well. And what happens in redox reactions, or oxidation reduction reactions, electrons are transferred from one substance to another. The substance that loses electrons is oxidized. Okay, so oxidation is a loss of electrons. So we say that in this reaction, the oxidation of A manifests as the loss of electrons, and A is oxidized. And the reduction of B manifests as the gain of electrons, and B is reduced. So this is the oxidized form of A, and this is reduced form of A. For instance, the green color of the Statue of Liberty is due to the oxidation of copper by oxygen. It forms green copper 2 oxide. Another example of oxidation and reduction reaction is reaction between the solid zinc and copper ions in a solution of copper sulfate. So in this situation, copper gains electrons and is being reduced, so it goes from copper 2+ to copper 0, while zinc loses electrons, becoming oxidized, becoming zinc ion with 2 positive charges. In biological systems, oxidation and reduction play an important role for their function. For instance, the various molecules can lose 2 hydrogens and 2 electrons, and coenzyme FAD will accept those 2 hydrogens and 2 electrons. So in this situation, biological molecule that loses 2 hydrogens and 2 electrons become oxidized, while the coenzyme FAD, when it accepts 2 electrons and 2 hydrogens, becomes reduced. So you can see that FAD, it's a reaction of oxidation of biological molecule, loss of hydrogens and electrons, but at the same time it's a reduction of coenzyme FAD, gain of hydrogens and electrons. In many biochemical reactions, the hydrogen atoms have to be transferred between the molecules as well. So in this example, for instance, when methyl alcohol is oxidized to formaldehyde, methyl alcohol loses hydrogens. When formaldehyde is converted to formic acid, formaldehyde is oxidized via the addition of oxygen atoms. And when formic acid is oxidized to CO2 in water, it is oxidized by addition of oxygen atoms. I want to make it very, very clear. In each of these reactions, there is a transfer of electrons. So methyl alcohol, when it is oxidized to become formaldehyde, it loses electrons. Formaldehyde, when it is oxidized to form formic acid, it loses electrons. Formaldehyde loses electrons. Formic acid loses electrons when it is oxidized to CO2 in water. But for the convenience, we often use the following rules. So oxidation always involves loss of electrons, but can be seen as an addition of oxygen or loss of hydrogen. the reduction always involves a gain of electrons, but can be seen as the loss of oxygen or gain of hydrogen. So let's talk about some chemical quantities and reactions and how we calculate chemical quantities. So in a chemical reaction between the iron and sulfur, iron 3 sulfide is produced. So here's the reaction. 2 atoms of iron interact with 3 atoms of sulfur, producing 1 molecule of iron 3 sulfide. Reactions are described by the law of conservation of mass that indicates in an ordinary chemical reaction, matter cannot be created or destroyed. There's no change in total mass. And the mass of products here is equal to the mass of reactants. So in this reaction, where 2 atoms of iron interact with 3 atoms of sulfur, forming 1 molecule of iron 3 sulfide, it can be read this way. 2 moles of iron interact with 3 moles of sulfur, forming 1 mole of iron 3 sulfide. So mole-mole factor is a ratio of the moles between any 2 substances in an equation. So for instance, mole-mole factor for iron and sulfide is 3 moles of iron per 3 moles of sulfur, or vice versa. Mole-mole factor for iron and iron 3 sulfide is 2 moles of iron per 1 mole of iron sulfide, or vice versa. The mole-mole factor for sulfur and iron 3 sulfide is 3 moles of sulfur per 1 mole of iron sulfide, or vice versa. So let's see how we can use this knowledge in the calculations. So the question is how many moles of iron 3 oxide can form from 6 moles of oxygen. So this is the reaction for oxidation of iron, and the mole-mole relationship here is that 3 moles of oxygen correspond to 2 moles of iron 3 oxide. So we use a conversion factor. 2 moles of iron 3 oxide correspond to 3 moles of oxygen. We multiply it by 6 moles of oxygen, and what do we get? 4 moles of iron 3 sulfide. Now, we can expand this practice into so-called mass calculations for reactions. For instance, being able to do mass calculations for reactions, we can quantify the mass of acetylene that we need to use to weld a specific mass of metal. So basically, in a balanced chemical equation, we can convert the mass of one substance to the mass of another substance via following steps. First, we need to convert the mass of substance A to moles, since we can calculate the molar mass of A. Then we can convert the moles of substance A to moles of substance B, using the mole-mole factor or mole-mole ratio between B and A in a balanced equation. And third, we need to convert the moles of substance B to the grams using the molar mass of substance B. Let's take a look how we can do that. So this is your steps, but we're going to look at the actual example. So let's say we have a reaction where nitrogen interacts with hydrogen, forming ammonia. We need to know the mass of ammonia that can be produced from 32 grams of nitrogen. So this is what we have. This is what we need. So we're going to start with writing a plan. So we're going to convert grams of nitrogen into moles of nitrogen using nitrogen's molar mass. Then we're going to convert moles of nitrogen into moles of ammonia using mole-to-mole factor. And then we're going to convert moles of ammonia into grams of ammonia using the molar mass of ammonia. So let's take a look. 1 mole of nitrogen weighs 28.02 grams. So these are conversion factors for mole of nitrogen into grams of nitrogen and vice versa. This is the mole-mole ratio between the nitrogen and ammonia. So 1 mole of nitrogen corresponds to 2 moles of ammonia, vice versa. And here's the conversion for ammonia, from moles to grams. We know that 1 mole of ammonia weighs 17.04 grams, or vice versa. So let's see what we've got. 32 grams of nitrogen, we multiply it by the first conversion factor. 1 mole of nitrogen weighs 28.02 grams. Then we multiply the product by the mole-mole ratio, 2 moles of ammonia per 1 mole of nitrogen, because the answer here is moles of nitrogen. And then we multiply it by the grams of ammonia per 1 mole of ammonia. The result, you can do it in one equation or you can do separate processes, it doesn't matter. But here's, you've got your mass of ammonia that will be produced following this reaction where 32 grams of nitrogen participate. Finally, let's talk about the role of energy in chemical reactions. I plan to describe exothermic and endothermic reactions and discuss the factors that affect the rate of a chemical reaction. So, for the reaction to occur, 3 conditions must be met. First, the reactants must collide. Then, reactants must align properly to break and form bonds between individual atoms, orientation condition. And finally, the collision must provide the necessary energy of activation. The reaction is exothermic. The heat is released. And in exothermic reaction, the energy of the products is less than the energy of the reactants. Heat is one of the products. For instance, when there is a reaction between the carbon and hydrogen, and the methane is formed, the heat is produced. It's the exothermic reaction. In endothermic reaction, the heat is absorbed. So the energy of products is greater than the energy of the reactants, and heat is the reactant. It is added to the reaction. For instance, in the reaction of oxidation of nitrogen by oxygen to form nitrogen oxide, the heat has to be added, and the left has to be added to the reaction to make it run. Now, the reaction rate is the speed at which the reactant is used up, or the speed at which the product forms. It increases when temperature increases. It happens because the reacting molecules move faster, which results in more collisions between the molecules that will satisfy the requirement of having an energy of activation. And same happens when you increase the concentration of reactants, because there will be more collisions between molecules with energy of activation. The catalyst, special chemical that does not participate in the reaction, it increases the rate of the reaction by lowering the activation energy. You see, the activation energy is a bit of a hump that the reaction has to go over, and catalyst decreases the activation energy. And catalyst is not used up during reaction, it remains unchanged during the reaction. So at the end of the day, I want you to know 3 factors that increase the reaction rate. Increased concentration of reactants, which results in more collisions. Increased temperature, which results in more collisions, and more collisions specifically with energy of activation. And catalyst, which lowers the energy of activation.